Hi, my name is Jeff Bush. I've been a long-time gamer, so I've been very excited to see the way that mobile gaming has really exploded. And I'm even more excited to see that Palm is really taking a lead in this area. If you want to have a great application development environment and a game development environment, it's not sufficient just to have a GPU and be able to download games over the air. There are three things you really need to have a good mobile gaming platform, and Palm is one of the few companies that's positioned to provide all of them. You need to have a good catalog, and Palm has a really compelling offering. We have a turnkey option, which allows you to upload applications to our developer portal. After a short review process, the application will show up on the application catalog application, which is on all of our devices, which means every user can go, they can search for applications, download them, and install them. However, we've recently also introduced a web distribution model. This is similar to the other option, except instead of going through the review process and showing up in the catalog, you upload an application and we give you a URL. You can distribute this however you want. You can put it on your website. You can send it through email. You can even embed it in other games. When a user clicks on that, they can install the application. We've also recently opened up feeds of all of the titles in our catalog to third parties. So a third party can actually create their own catalog interface. So there's a lot of ways to get applications to your users. But you really need compelling applications. And in order to do that, you need strong technical underpinnings. All of our devices are based on the latest hardware with top-of-the-line ARM CPUs, the latest generation, and hardware acceleration resources like GPUs and media decoding. A logical consequence of having powerful hardware is that you can run a desktop-class operating system on the device. What we've learned is that it's very hard to take an operating system that was designed 15 years ago and make it scale up to the hardware that you have right now. Because of this, we based our kernel on Linux. Linux is a mature, very high-end operating system. It scales all the way up to supercomputers, has protected memory, a lot of the other features that you expect, a full-fledged standard libc. You don't have to worry about arbitrary heap limits or running out of handles. It's like a desktop operating system. On top of this, we developed all of the upper layers of the stack from scratch. We targeted advanced hardware from the inception, and we made optimizing for developers one of our key design priorities. The final thing you need, and this is a thing that I think doesn't show up as much on marketing slides and people don't talk about, but is one of the biggest drivers of success, is having the right tools and development environment. Our design from the beginning was optimized to make developing applications easier, and that's why we went with the rather unique model of application development that we did. But we've also been doing new things recently, like the groundbreaking Project Ares, which actually allows you to develop applications completely in a web browser. Allows you to drag and drop controls and edit your JavaScript code right there. Now with the PDK, we're trying to bring that same philosophy of easy development to developing with C and C++. Now, the most important thing is really that we've developed a platform. It's not just an operating system, it's not just a hardware platform, and it's not just a cloud service. It's all of these things, and they're designed to work together. And because of that, it becomes more powerful than each of those things individually. So I wanted to show you a little bit of what this is actually capable of. A little less than 2 weeks ago, actually, we're talking to our friends over at Epic. And we said, it'd be kind of cool to actually bring Unreal Engine over to the WebOS and see how it did. Unreal, if you're not familiar with it, I'm sure most people here are, is behind a lot of their Epic's own titles, Gears of War, Unreal Tournament, but has also been licensed extensively to other ones. It was developed as a desktop engine, so it's very high-end. It uses a lot of advanced features. You can see, actually, if we look through the app, if we look at the app, we can see that it's using a lot of advanced lighting. The environments are very detailed. It's a high polygon count, so it's a very good test of really the capabilities of this device and showing what a high-end platform can do. The other thing that's interesting about it is how fast we could bring it up. We really less than 2 weeks ago, we began working on porting this, and it was just one engineer, and came over really quickly. It shows the power of the APIs, and we didn't have to spend a lot of time mucking about with the actual glue code, we could actually just bring things up very quickly. And you can see it looks beautiful. So, in January, we announced that we were making this thing called the PDK. And we didn't tell you a lot about what it was, but we did introduce a number of AAA titles from companies like Gameloft, Glue Mobile, Electronic Arts, and Laminar. And we'd like to give you a lot more details today. So as I said, Palm application development is based on web technologies, HTML, JavaScript, CSS. When we looked at what was happening in the mobile industry, we saw that the thing that was really driving these devices and making them interesting was the fact that they could connect to the cloud and that they could get stuff off the web. And it made a logical sense to actually embrace those technologies and make them be the native development platform. On top of this, we built a UI toolkit called Mojo that had a lot of standard controls and things that the application developers wanted. Text entry boxes, buttons, things like that. The PDK extends this to allow cleanly mixing C and C++ compiled code with web applications. It allows you to use the most appropriate tool for the task. At Palm, we believe in giving developers options because ultimately you have to make the decision about how you want to build your application. We believe that the future of mobile is really the web, and this is an excellent complement to that. So a plugin is basically just a compiled executable. It takes up space on the page. It participates in the layout of the page. And this is kind of the cool thing about the fact that we chose HTML as a technology. Most interpreted environments have a mechanism of calling into native code, and they build all of their primitives on top of that. But usually it's kind of hidden. The really interesting thing about using HTML is that embedded objects are first-class objects. They have defined mechanisms of taking input, of how they draw, of how they composite. And so it becomes very easy for those things to mix in and become library of objects. Now, to be clear, developing in C and C++ is more complex than JavaScript. And there is more complexity there, and there's more work because you're not in a nice runtime environment with garbage collection. But there are a number of reasons why you would want to use C and C++. The first is you may want to leverage a specialized code base. In many cases, you may already have made an investment into a code base. And we don't want you to have to throw that away to come over. So examples of this include signal processing, navigation algorithms, physics. Another thing is that you may need capabilities that are not yet standardized on the web. We're very excited about a lot of the things that are happening in the mobile web space. WebGL, actually, they've been doing a lot of stuff with that, and you see things like O3D. We've joined a lot of standards bodies, actually, to help drive these things, like Khronos. Over time, you're going to see more and more of this stuff coming into web. And it's not just us that's driving this. We didn't invent the idea of having web-based applications. We saw this as an industry trend and something that's happening that a lot of companies are doing. And so we can really leverage a lot of the things that they're doing. And we realize basically that the web is evolving, but everything is not there yet. The third reason you may want to use C and C++ code is because you may have a compute-intensive task. And I think it's useful to mention at this point that we use the V8 JavaScript engine. It actually translates the JavaScript into machine code and executes that directly. It's one of the most advanced and fastest interpreters around today. But at the same time, sometimes you really just need to get down to the metal. So based on what we've said, there's really limitless permutations of how you could structure an application with the PDK because you can mix and match the components. But I wanted to look at a few use cases to give you a better idea of how the PDK fits in with the regular API. So the first case is probably everybody's familiar with, is the full screen case. Basically, if you make a plugin, take up the full screen, it has direct control over drawing, a very direct drawing path to hardware, has direct access to all inputs. There's no kind of extra need to actually thunk through any kind of extra layers. Very high performance, and you've seen that we've been able to bring over a lot of really high-end games. And this is the model that probably a lot of game developers at first will be like, that's probably the one I'm interested in. But it's not necessarily the only one, and actually there are a lot of reasons to use other models for games, which we'll talk about. The second case is the idea of having inline content that we actually mix with HTML. Now, this is actually, interestingly, not a new concept to WebOS. It's existed since the very first version that we let out. And one example of that is our built-in navigation application. Now, the nav app is not a game, so If you've been having trouble getting past the first level, that's why. I think it actually illustrates a number of concepts that transfer very well to game development and things that actually developers have asked us for. So we'll give a kind of example of how this works, and I'll talk about how the components fit together. So when you go to the nav app, you want to search for a place that you want to go to. So you enter in an address. You can see that it has an auto-completion. It's actually dynamically fetching from the server and giving you suggestions. And then when you actually tap and click enter, it goes and it downloads a list of the locations. So this is all done using HTML and JavaScript. And that's probably the right way to do it. I mean, if you've done programmatic layout in C++, it's a pain. And doing this in a low-level language, it's a lot more work than doing it in HTML, which really does all this stuff natively. So, it's much easier to do it using this and do the list layout. But then when we actually want to go somewhere on here, we tap one of these. A new view comes in, and at this point, this is actually being drawn by native code. You have the navigation algorithm is choosing routes. You have kind of a 3D display there. But say, for example, I can tap on it. I can get a list of options. And if I do that, this control comes up. But this is actually widgets that are written using JavaScript and HTML. You can see that they mix seamlessly. It's not obvious. And one of the interesting things is we showed this slide to some people who were like, oh, this is a slide. And they said, well, it's a little confusing because it's not clear which is actually the PDK and which is HTML. And I'm like, that's the beauty of it. There's not this hard boundary, and they mix very cleanly. The final use case is probably one that's more common with other types of native environments, and basically it's a hidden plugin. It doesn't do any drawing. It's like a library of functions. Examples of this would be things like signal processing, doing voice recognition. And it's interesting to note now, media capabilities are something that exist in kind of a very early form in the current version of the PDK, but it's something we want to work on. We think there's a lot of potential there to do some interesting things. So let's kind of look under the hood a little bit at what exactly is in the PDK. So we'll start with kind of our obligatory stack of boxes. The bottom, we have our hardware resources. We have the CPU. We have a lot of our hardware accelerators with graphics, media decoding. Those are all wrapped by the Linux kernel and exposed by the driver model. For doing HTML and the majority of development, we have the app lives in a process. It sits on top of WebKit, industry standard, really now HTML rendering. Our framework sits on top of that, and then the application runs on top of the framework. When you want to start a plugin, the plugin lives in a separate address space, and there's a number of libraries that it can sit on top of that actually interface directly to the low levels of the system. We have a standard C and C++ library. This includes the standard template library, pretty much everything you'd expect from a desktop environment. OpenGLES 1.1 and 2.0, fully hardware accelerated pipeline, programmable shaders, Vertex and Fragment, so very advanced graphics hardware. Kind of the heart of the PDK is SDL. SDL is a simple direct media library. It's a fairly mature, open source, cross-platform library oriented towards games, but relatively flexible. It provides a lot of basic functionality like event handling and initialization. We also bundle a number of utility libraries in here that are associated with this, like SDL Image, which allows you to easily decode pings and JPEGs and bitmaps. SDL Mixer, which is a high-level audio API that allows you to play sound effects, background music. You can load up a bunch of sounds and fire them off asynchronously. SDL TTF that allows you to render TrueType fonts, and a lot of other things in there. And finally, we have something we call the plugin device library, which gives you access to functions that are device-specific or aren't necessarily covered anywhere else, like controlling backlight dimming and things like that. And the plugin executable just runs on top of these libraries and basically can communicate with the application process. So let's write some code. So we started out kind of looking at this, and we said, we need some kind of we need a solution for being able to develop on a desktop environment, because you don't want to have to be pushing stuff to the device to do all of your development. And we talked about, do we need an emulator or an armulator or a simulator? And what's the difference between a simulator and an emulator? And we've thought about it a bit. We're like, well, the reason you run a simulator in most environments is because the thing that you're actually simulating is so different than the desktop environment. But we really are very similar to a desktop, and we really have a desktop environment. So what we said is, why don't we take the libraries that are on the device and just compile them for the desktop? Then you could run a native application on the desktop, and it'll behave much the same way. The advantage of this is it allows you to use a lot of the tools that you're already familiar with. Your IDEs, a lot of your debugging tools, you can just execute them there. So this is Visual Studio. You don't have to use Visual Studio. You could use Eclipse. People seem very polarized. They love one or the other. We'll open this. This is the sample application that actually comes with the PDK. I'll go up here to debug, and I'll say start debugging. It'll ask me if I want to compile. And there comes the app. So the dimensions of this window match the dimensions of the device. It'll respond to touch inputs. I can emulate them with the mouse. It's a fairly close approximation of what's running on the device. But the nice thing is, since I'm running in this environment, I can set a breakpoint. I can single step. I can look at my variables. And I can develop pretty much the way you expect to on a desktop. But our goal is really to be able to run it on the device. So what I've done here is, in the Tools menu, I've added a little shortcut to a script, which is something you can do in Visual Studio, called Run on Device. And I'll click this now. Okay. So a lot just happened really fast there. So let's slow down and actually walk through what happened there. You can see that the same application is basically running there. So if I look in the commands that are sent here, we do a couple things. So first, we need to compile the application, and we provide standard GCC tool chain. It doesn't have to live in any special environment like Cygwin. It's just a native Windows executable. In this case, I've launched it directly from a script, but you could easily integrate that into whatever build system you want to use, be that Ant or Make or any of those, Jam. And I create an executable which is called Simple. Now, the way that we actually handle connecting to the device is we simply tunnel TCP sockets through USB. So that means you can use standard services to actually access processes on the device. In this case, if you're familiar with Unix, we're going to use something called secure copy, which is a very common Unix command for copying files between servers. And in this case, we're just going to copy this onto the device's internal file system. And finally, we go ahead and we can use another service, standard Unix service called Secure Shell, and execute that command on the device, and then it pops up. So an interesting thing about this is we wanted to make the edit, compile, test cycle as fast as possible. And nothing's more frustrating for a developer than sitting and just waiting for your tools, or you have to go bug somebody else or get a coffee because you can't actually spend your time developing your application. It was very important for us to make these fast, low friction, and very easy to use and integrate into other environments. Now, obviously this is a small app. Bigger ones will take longer to compile, but it was less than a second. It was very quick. And so, for example, if I wanted to go in and change this, so let's say I wanted to make this shape be yellow, right? So I see it looks like we've hard-coded the color into the shader here, so I'll just go change that. If we look at the device, I'll just go Tools. I'll use my Run on Device script again. And there it is. So like that, you can make changes and iterate very quickly on that. So one question you may be asking is, do you have the ability to actually, we can symbolically debug on the desktop. Can we symbolically debug on the device using Visual Studio? And the answer is, well, not yet, but we're actually fairly close. We are working on a Visual Studio plugin that will allow you to symbolically debug on the device. If you are an Eclipse user, however, we actually already provide pre-configured Eclipse workspaces that will connect to the device and give you symbolic debugging, including viewing symbols. Now, depending on what kind of user you are, we also allow you to go to the shell. So I have the standard Unix shell on the device. I can use all the commands that I'm used to. I can look at the CPU usage, top, copy things, make scripts. Very powerful, easy to use. So basically what we've done is we've provided a solution that's very clean, turnkey. We give you things that work right out of the box, but they're also developed in a way that it's very easy to adapt to your own environment. So let's go to an example that's a little more complex. So this is basically a simple particle simulation. It doesn't do a whole lot. It gets a little boring quick. We'll fix that in a minute. But first, maybe we'll actually let's look at the structure of the code and see how this actually works. So the entry point is main, just like you're used to. We come into to here, we call into init.SDL, which is a function we defined. We call SDL init. We pass it some flags to tell it what we want to initialize. In this case, SDL init video says, we want to be able to use graphics. Fairly straightforward. Then we come into the main event loop. At the top of the event loop, we can check to see if there are any events in the event queue, and they'll fill in this event structure. And we can switch on the type of event. In this case, the only event I have is SDL quit, which gets sent to the app if the user dismisses it using their finger. But you could put keyboard handlers in there, multi-touch is supported, pretty much anything. Then we update the game state and render the frame using standard OpenGL calls. Call SDL GL swap buffers, which actually pushes it onto the screen. And that's about all there is to it. So what I'd like to do is actually implement an accelerometer in this, so we can actually control them and they actually respond to gravity and tilt of the device. So the way I'll do this, basically the way that we've implemented the accelerometer is we've exposed it using the joystick abstraction. Joystick is a very high-level abstraction. It really just represents a set of axes. So we said, that's essentially exactly what an accelerometer is. So the first thing we'll do is we'll just go in here to the initialization, and we'll say, okay, we want to initialize joysticks. And what this will do is turn on the accelerometer. It'll start sampling at a pretty fast rate, so we'll get responsive changes. Then I need a joystick object that I can actually interact with. So I'll instantiate joystick here. 0 is our accelerometer. And then in the loop here, I'll actually go and grab the values from that to do the update. So we'll say we'll access 0 as x. We'll normalize this since it's a short value. And then we'll do the same thing for the y-axis. And we'll turn that. And now we'll compile it. All right, no errors. Now, we don't have an accelerometer that's conveniently accessible on the desktop. So what we've done is the compiled version of our desktop libraries give us the ability to emulate some of the inputs on the device. In this case, I'll just hold down Shift and I move the cursor around, and now the particles respond to gravity. Fairly straightforward. Now, let's actually try to run it on the device. So I go back to my handy script, run on device. Click there. You can see it compiles it in the window there. There's the same application, and now I can tilt it, and they respond. So basically, 4 lines of code. I've enabled accelerometer for the app, and I didn't have to use a single bracket. So we've been talking a little bit about plugins, and so these have been fairly straightforward full-screen apps. So we should show you how we would actually develop something that interacts with JavaScript. Now, the model I've been using so far is to basically just compile an executable, push it someplace on the device, and execute it there, which is convenient for simple applications. And it's also nice if you're developing a large application that has hundreds of megabytes of resource, you don't want to have to bundle it up and reinstall the entire app every time. So it's convenient just to be able to push that one file. But in this case, we have a number of files. We want to push some JavaScript, some HTML, some native stuff. So it's convenient in this case, and it's a good excuse for me to show you how the packaging tool works. So what we'll do, I'm going to actually move to the command prompt a minute here. And what we'll do is we have a script in here called package it. It runs. It compiles this plugin. It bundles up all the resources. And you can see we now have a file here called Shapespin. So this is an iPackage. iPackage is a standard Linux installer format. It's basically a bundle that has all the things you need and it can be installed on the device. So now that I have it here, if we look on the device, I'll go ahead and just actually install that. And the way I can do that is we have a tool called PDK install. And if you look right there, you can see that a new app's just popped up. So very quick. Now I'll go ahead and tap this app and start it. And we can see now we have two things on the screen. So at the bottom, we have our old shape that spins around. And at the top there, we have a slider. And that slider is actually done completely using HTML and JavaScript. So what we want to be able to do is actually hook the slider up so that it can interact with that code. So let's take a look at this. So first of all, I'll just show you very quickly how we actually create this scene. So if we go into the views, we'll go ahead and open up the HTML file. This is the layout. So this is all you need to basically specify that layout. At the top, you can see we specify a div. That creates that slider element. And then below that, we have an object tag that represents our embedded plugin. Now, we can pass arbitrary parameters in here. We've given a couple examples. The most interesting one here is the exe. And this actually points to a plugin. Now, here's what I think is kind of cool about this. The plugin itself, it's not like a shared library. It doesn't have these weird dependencies where it won't kind of run on its own. It's a standalone executable. And so you can test it by itself. You can work on it in isolation. When you specify the exe here, when the HTML environment spawns it, the plugin then knows, I'm now inside this page. I need to composite into this page. I need to be able to get inputs. It works automatically. And the benefit of this is that you get less coupling between them. It's more object-oriented, and it's easier to develop because you can debug your individual pieces in isolation without having to set up this huge intricate thing. So in this case, we have this plugin. We'll name it here. It's called Shapespinner plugin, so it has an ID, which we'll use to reference it later. So what we want to do is actually expose a method to JavaScript from this plugin. And when we go into the plugin code, we'll open this up. Looks very similar to the other one, but we've added a couple of extra calls here, right here. PDL register Mojo handler. So what we've done is we passed two parameters, and the first one is the name of a method that you'd like to be exposed from your plugin object. And the second one is a C callback that should be invoked once that method is called. I'll go up to the top and we'll look at this callback, set rotation speed. Fairly simple. We get this object that basically is a proxy for the parameters. We can check to make sure that there are enough parameters, and then we can just actually get the value of that parameter, index 0, and convert it to a double. And that gives us the position of the slider, which will tell us how fast this should rotate. And then we adjust as much. Now with these hooked up, let's see how we actually would invoke that from JavaScript. So if we go into the application, we'll go into the controller. We call this an assistant, but it's basically the JavaScript code that provides all the behavior for the app. And in this case, handle slider is an event that gets called whenever the slider value changes. And all we need to do is we look up the plugin within the DOM tree, set rotation speed, and then we pass the value. So very clean, very easy. And once it's all put together, you can see on the device, I can actually just go in here, grab the slider, and the rotation of the object changes. And I can change the speed. So very quick, responsive, and very easy to interface between the two worlds. So we've shown you a few things today. We've walked through the tools and how the workflow works. We've given you descriptions of the APIs, showed you the general philosophy, how those work. But what we think is pretty cool is that the APIs are straightforward enough that with a minimum investment, you can bring apps very easily over to the platform. It has very powerful capabilities, and we expose these very openly so you can take advantage of all of them. And we have a really robust App Store solution, which gives you the ability to distribute your application. In January, when we first announced this with our partners, we had 7 applications that we had developed, just kind of really almost as a test. And since then, our developer partners have actually introduced 20 more titles. So this shows a couple things. I think this is really exciting. The first is it's really easy to bring apps over. The second is these guys love this, and there's a lot of momentum, and they've really seen the value of being on this platform. So what's next? So earlier this week, we introduced the first beta of the plugin development kit. Not everything is there, but we really wanted to allow developers to get early access to this, to see what's going on, and be a part of the process. We will be introducing updates pretty regularly to the PDK and the documentation. Currently, because things are still in flux, we're not allowing general distribution of apps that are built on the PDK, but we're currently targeting middle of the year to have that enabled so anybody can use the PDK and upload their apps. I'd encourage you to check out developer.palm.com. We have documentation. We have sample code. We're adding more there. There's a whole forum, and we have dedicated developer support engineers who are on the forums. A lot of the engineers who are working on the project are actually on these forums. So, it's a great place to both get your questions answered and also give feedback and help kind of influence the process. So, if anybody has any questions. The question was free phones. No, I don't think we have any free phones today.
So you said that you're looking at general release PDK apps in mid-year. Is that when it's going out of beta?
The question was when are we're looking at general apps. Yes, the answer is middle of the year. We're expecting anybody to use the PDK, to be able to use the PDK in their applications. We don't have an exact date. The reason that we didn't initially come out with a Linux version was, a lot of our partners were actually using Windows and Mac. So, but I think fairly soon, hopefully.
What kind of networking support is in the PDK?
That's a good question. I actually glossed over that. So the question was what kind of networking support is in the PDK. So pretty much full networking access. We do expose the kind of POSIX sockets layer, BSD, from Linux. You can open arbitrary TCP and UDP sockets as allowed by your carrier. And there's also a library called SDLNet, which is a series of cross-platform network convenience functions that let you access that. And actually, recently we've just added a few games to the catalog that use networking. If you go by our booth, they're actually playing a networked Shrek cart. They can race each other at the two stations. So. Yeah. Some time. So actually, if we want to, do you want to go back real quick, and I can actually just walk through it? So basically, we just emulate multi-touch as a mouse event. So what we could do here is, I think if we said something like this. And what we can do is actually, if we look inside the event structure, we'll see that there's a motion event. It's a union. And within there, we have an X and a Y, which show the position of that. But we also have a which. So what we can do is actually just get the finger number. So what will happen is you put finger 1 down, you'll get a mouse down, and it'll have an index of 0. You put a second finger down, it has an index of 1. And you can basically have up to 5 fingers with that method. Does that make sense? So the question is, do we have any kind of protections because the apps have pretty direct access? Yes. So, I mean, that is part of the reason why the PDK is not ready yet. The nice thing about running, well, there's two kind of things that really help us here. First of all, we're running on Unix, which has a long security pedigree. It's really designed to be able to isolate processes. And we run each plugin in its own process. So we have a lot of tools that we can use to do that. And so one of the things the final version of the PDK will have is a lightweight security sandbox, chroot jail, and it'll basically restrict it to using only the things that it should be using. Oh, sorry.
Even with the remote, people is not allowed at this point. Can we run GDB server on the platform?
Oh, yeah, and it is actually allowed. I don't know if I wasn't clear about that. So the question is basically, can we do remote debugging? So there's a couple ways you can do this now. So there is actually GDB on the device. If you like the command line, you can just use it directly from the device. We do already have a GDB server, and in fact, if you install the PDK as it is, you can we'll install an Eclipse configuration that actually has all the scripts. You just click Go. It'll start the server automatically using SSH and completely connect, and that gives you full symbolic debugging. So you can do that now.
Which SDL version is it based on? 1.2 or 1.3?
That's a good question. It's 1.2. And we're looking at 1.3, and that's still a ways off. But we've actually been talking to Sam about which way that's going and looking at pulling things of that in. Any other questions? Well, the question is, are we talking to Unity? And I guess I can say it would be fairly easy probably for Unity to run in this environment. I can't talk about any specific plans, but certainly it would be interesting. Any other questions? Yes, the question is basically the resolution independence. So yeah, there's a method you call. It'll give you the screen dimensions. Pixie is 80 pixels shorter than the pre, so a little bit different. Generally, we advise in our documentation people to try to write things to be resolution independent, which is doable if you basically do your computations using the screen size. And generally we advise people to kind of write for something that will work on both. And for the most part, if you compile straight ARM, it'll work on both platforms. The GL library is binary compatible, so the same executable will run on both. If you need to really take advantages of a higher end platform, that is possible to do, and we have ways in our catalog of tagging which specific architecture something's for.
Are both devices GLDS 2.0?
Yes, they are. One of the advantages of coming in just a tad later was that we could unify on 2.0. And it's a big problem and with other devices that they're 1.1 and 2.0, and they're really nary the two shall meet. So I'm excited. I mean, that's one of the reasons we were really excited about working with Epic and getting Unreal up, because it is a 2.0, really demonstrates that stuff. And we're really excited to see more 2.0 type apps because they look really cool. Oh, yeah. The question is, you want a developer device that you don't have to buy a contract for, and that's actually. Do we have that?
Yeah. So I work at Palm to develop relations.
I just asked this random guy in the audience.
Yeah. So I can sort you one right here if you want. But yeah, we've got a device program that we're putting together. We've slowly kind of released different things out of it, so you can feel you'll see a lot of stuff on that.
Yeah, you could probably, maybe, well, probably not. I was going to say you could sell that Android phone, but I don't know. Any other questions? Okay, great. Well, thanks for taking the time to check us out, and I hope you go to the website. A lot of interesting stuff there. You should just try it out and play with it. It's fun. You can actually kick the tires without having a device. You could just run it on the desktop and see how it works. All right, thank you.